What if I told you that one of the greatest minds in physics discovered something so profound about the universe that it completely changed how we understand the Big Bang? Richard Feynman, the Nobel Prize-winning physicist known for cracking the secrets of quantum mechanics, stumbled upon a truth that would shake the very foundations of cosmology. And what he found wasn't just about what happened during the Big Bang. It was about what came before it, before time, before space, before everything. Stay with me, because by the end of this video, your understanding of reality itself will never be the same. For decades, we've been told a simple story. The universe began with a massive explosion, the Big Bang. Everything that exists, all the galaxies, all the stars, all the planets, even time itself, started from a single point, roughly 13.8 billion years ago. But here's the thing, that story is incomplete. And Richard Feynman knew it. Before we dive into what Feynman discovered, we need to understand why the Big Bang theory had a problem in the first place. A problem so significant that physicists couldn't sleep at night thinking about it. You see, when scientists talk about the Big Bang, they're describing a moment of infinite density and infinite temperature. A singularity. But here's where it gets weird. Physics completely breaks down at a singularity. Our equations don't work, our understanding of nature fails. It's like trying to divide by zero. You just can't do it. Einstein's theory of general relativity, which beautifully describes gravity and the large-scale structure of the universe, tells us that if we rewind time, the universe gets smaller and smaller until it reaches this point of infinite density. But Einstein himself was uncomfortable with this idea. He knew that infinities in physics usually mean we're missing something important, that our theory is incomplete. On the other side, we have quantum mechanics, the physics of the very small, which Feynman helped develop. Quantum mechanics governs atoms, particles, and the fundamental forces of nature. And here's the problem. General relativity and quantum mechanics don't play nice together. They're like two different languages trying to describe the same thing. When you try to apply both at the same time, especially at the extreme conditions of the Big Bang, everything falls apart. This is where Feynman enters our story. In the 1940s and 1950s, Feynman was revolutionizing physics with his path-integral formulation of quantum mechanics. This wasn't just another mathematical trick. It was a completely new way of thinking about reality. Instead of asking where is a particle and what path does it take, Feynman said something radical. A particle doesn't take one path, it takes every possible path simultaneously. And the path we observe is just the sum of all these infinite possibilities. Think about it like this. If you throw a ball from point A to point B, common sense tells us the ball follows one curved path through the air. But in Feynman's quantum world, that ball simultaneously takes every possible path. It goes straight up and comes down, it curves left, it curves right, it even goes backward in time and forward again. Every path you can imagine, the ball takes it. The path we actually see is determined by adding up the contributions of all these infinite possibilities. Now you might be thinking, that's insane. And you're right, it is insane. But it's also experimentally verified. This is how nature actually works at the quantum level. And Feynman won the Nobel Prize for developing these ideas. But Feynman didn't stop there. He started thinking bigger, much bigger. If particles can take every possible path, what about the universe itself? Could the same principle apply to the entire cosmos? Could the universe have taken every possible path to get to where it is now? This question led Feynman to explore what's called quantum cosmology. And this is where things get truly mind-bending. If we apply Feynman's path-integral approach to the entire universe, we have to consider every possible history of the universe, every possible way the universe could have evolved from its beginning to now. And just like with the particle, the universe we observe is the sum of all these possibilities. But here's the kicker. If the universe can take every possible path through time, what happens when we reach the Big Bang? What happens at time zero? Feynman realized something profound. The question, what came before the Big Bang, might not even make sense. Not because there's nothing to know, but because time itself behaves differently at those extreme conditions. Let me explain. In our everyday experience, time flows in one direction: past, present, future. This is what we call real time. But in quantum mechanics, and especially in quantum cosmology, physicists often work with something called imaginary time. Now, don't let the name fool you. Imaginary time isn't fake or made up. It's a mathematical concept where time behaves more like space. Feynman showed that when you apply quantum mechanics to the universe at the moment of the Big Bang, real time and imaginary time can interchange. Time becomes a dimension like space. And in this framework, asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because you've reached a boundary where the normal rules don't apply. This idea was later developed further by Stephen Hawking and James Hartle in what's known as the Hartle-Hawking no-boundary proposal. They built directly on Feynman's path integral approach. They proposed that the universe has no boundary in imaginary time. It's finite but has no edge, just like the surface of a sphere is finite but has no boundary. You can walk around it forever without reaching an edge. In this model, the Big Bang isn't a moment of creation from nothing. It's a transition, a point where imaginary time transforms into real time, where the quantum realm gives rise to the classical universe we observe. Time doesn't begin at the Big Bang, it emerges from it. And this means the question of what came before becomes meaningless, because before doesn't exist in the way we normally think about it. But Feynman wasn't done challenging our understanding. He also contributed to another revolutionary idea that addresses what came before the Big Bang: cosmic inflation. Now, inflation wasn't Feynman's idea originally. It was proposed by Alan Guth in 1981. But Feynman's work on quantum field theory, the framework that combines quantum mechanics with special relativity, provided the mathematical foundation that made inflation possible. So what is inflation? Imagine the universe in its first moments, not the Big Bang itself, but just a fraction of a second after. We're talking about 10 to the negative 36th seconds after the Big Bang. That's a decimal point followed by 35 zeros and then a 1. In this unimaginably brief moment, something extraordinary happened. The universe underwent a period of exponential expansion. It doubled in size, and then doubled again, and again, and again. In less time than it takes light to cross the nucleus of an atom, the universe expanded by a factor of at least 10 to the 26th. That's expanding from smaller than an atom to roughly the size of a grapefruit. This sounds crazy. But inflation solves some major problems with the standard Big Bang theory. Remember those problems I mentioned earlier? The horizon problem and the flatness problem? Inflation solves both of them elegantly. The universe appears uniform because all the parts we can see today were once in contact with each other before inflation blew them apart. And the universe appears flat because inflation stretched out any curvature that might have existed, just like blowing up a balloon makes its surface appear flatter. But here's where it connects to Feynman and the question of what came before. Inflation requires something called a scalar field. Think of it as an energy field that permeates all of space. This field has potential energy, kind of like a ball sitting on top of a hill. When the field is at the top of the hill, it drives inflation. As it rolls down the hill, inflation ends, and all that potential energy converts into matter and radiation, the hot, dense state we call the Big Bang. The mathematics describing this scalar field comes directly from quantum field theory, the framework Feynman helped develop. Without his work on how quantum fields behave, we wouldn't be able to describe inflation mathematically. We wouldn't understand how a quantum field could drive the exponential expansion of the universe. And here's where it gets even more interesting. In the inflationary model, the Big Bang as we traditionally think of it, that hot, dense state, isn't the beginning. It's the end of inflation. The actual beginning, if there even was one, lies before inflation, during a period we call the inflationary epoch. So, what was the universe like during inflation? This is where Feynman's quantum insights become crucial. During inflation, the universe was dominated by quantum fluctuations, tiny random variations in the energy of the scalar field. These weren't just small disturbances, they were the seeds of everything we see today. Every galaxy, every star, every planet traces its origin back to these quantum fluctuations during inflation. Feynman's path integral formulation helps us understand these fluctuations. In the inflationary universe, different regions of space take different paths through the energy landscape of the scalar field. Some regions stay inflating longer, others stop inflating sooner. This creates a patchwork of different regions with slightly different properties, and these differences, magnified by the expansion of space, become the density variations that eventually collapse into galaxies. But here's the truly mind-blowing part. Some physicists, building on Feynman's ideas, have proposed that inflation might not have a beginning at all. This is called eternal inflation. In this model, once inflation starts, it never completely stops. Sure, it ends in our local region, creating our observable universe, but in other regions, inflation continues. And in those inflating regions, quantum fluctuations constantly create new regions where inflation ends, spawning new universes, each with potentially different laws of physics. This means our Big Bang, the event that created our observable universe, might just be one of an infinite number of Big Bangs occurring throughout a vast multiverse. And this multiverse might not have a beginning. It could be eternal to the past. The question of what came before our Big Bang becomes what other universes exist alongside ours in this eternally inflating multiverse. Feynman himself was skeptical of some of these wilder ideas. He was famously pragmatic. He once said, "I would rather have questions that can't be answered than answers that can't be questioned." He believed in following the mathematics wherever it led, but also in staying grounded in what we can actually observe and test. And that's the key question. Can we test any of this? Can we find evidence for what came before the Big Bang? Surprisingly, the answer might be yes. The quantum fluctuations during inflation left an imprint on the universe. We can see this imprint in the cosmic microwave background radiation, that faint glow of light left over from when the universe was just 380,000 years old. Satellites like COBE, WMAP, and Planck have mapped this radiation with incredible precision, and what they found matches the predictions of inflation beautifully. The pattern of hot and cold spots in the CMB matches exactly what we'd expect from quantum fluctuations stretched out by inflation. This is smoking gun evidence that inflation happened. And if inflation happened, then what we call the Big Bang was really the end of inflation, not the beginning of everything. But scientists are looking for even more direct evidence. During inflation, the rapid expansion of space should have produced gravitational waves. These are ripples in the fabric of space-time itself. Unlike light waves or sound waves, gravitational waves can travel through anything. And the gravitational waves from inflation should have left a specific pattern in the polarization of the cosmic microwave background. Several experiments are currently searching for this signature. Experiments like BICEP, the Keck array, and future satellites like Lightbird. If they find it, it would be direct confirmation that inflation happened. It would be like finding a fingerprint left by the pre-Big Bang universe, a message sent to us from before time as we know it began. Feynman also contributed to another approach to understanding the beginning of the universe: loop quantum gravity. This is an attempt to merge general relativity and quantum mechanics into a single framework, a theory of quantum gravity. In loop quantum gravity, space itself isn't continuous. It's made up of tiny, discrete chunks, like pixels on a screen. These chunks are so small that billions of them would fit inside a single atom. When you apply loop quantum gravity to cosmology, something remarkable happens. The Big Bang singularity disappears. Instead of the universe collapsing to a point of infinite density, it reaches a maximum density and then bounces back. This is called the Big Bounce. In this scenario, our expanding universe came from a previous contracting universe. The Big Bang wasn't a beginning, it was a transition, a bounce from contraction to expansion. And here's where Feynman's path integral approach comes in again. In loop quantum cosmology, the bounce happens when quantum effects become important. The universe takes multiple paths through this transition.
Some paths bounce earlier, some later. The path we observe is the sum of all these possibilities, just like Feynman taught us. If the Big Bounce is correct, then before our Big Bang, there was a universe collapsing. And before that, perhaps another expansion. And before that, another collapse. The universe could be cyclic, bouncing back and forth between expansion and contraction eternally. No beginning, no end, just an eternal cycle. But Feynman would remind us to stay humble. He would say that we're dealing with questions at the very edge of what physics can describe. We're extrapolating our theories to conditions we can never directly observe. The temperature and density at the Big Bang or before are so extreme that we can't recreate them in any laboratory. We can't run experiments to test our ideas directly.
What we can do is look for consequences, predictions that these theories make about things we can observe. And that's exactly what modern cosmologists are doing. They're using the cosmic microwave background, the distribution of galaxies, the abundance of elements, and gravitational waves to test different models of the early universe. One of the most important lessons from Feynman's work is that nature is under no obligation to make sense to us. Reality at the quantum level is deeply weird. Particles exist in multiple states simultaneously. They can be entangled across vast distances. They can tunnel through barriers that should be impenetrable. This weirdness doesn't go away just because we're talking about the universe as a whole. In fact, it becomes even more pronounced. Feynman taught us to embrace this weirdness, to follow the mathematics and the experiments wherever they lead, even if it violates our intuitions. Our intuitions evolved to help us survive on the African savanna. They're not designed to understand the beginning of the universe or the behavior of quantum fields. We have to let go of our everyday assumptions and let nature tell us how she works. So what did Feynman really discover about what came before the Big Bang? He discovered that the question itself might be based on faulty assumption. Time, as we experience it, might not extend back before the Big Bang. Or it might transform into something we call imaginary time, where the distinction between before and after breaks down. Or there might be an eternal inflation, where our Big Bang is just one of countless events in a timeless multiverse. Or the universe might bounce, with our expansion following a previous contraction. All of these ideas build on Feynman's revolutionary insights about quantum mechanics, his path integral formulation, his work on quantum field theory, his insistence on following the mathematics and staying true to experimental evidence. Feynman didn't solve the mystery of what came before the Big Bang, but he gave us the tools to explore it. He showed us that the universe is far stranger and more beautiful than we ever imagined. Today, physicists continue to build on Feynman's legacy. They're developing new theories of quantum gravity. They're designing new experiments to probe the earliest moments of the universe. They're using supercomputers to simulate different models of cosmic history. And they're always keeping Feynman's spirit alive. Question everything, test everything, and never stop wondering. The quest to understand what came before the Big Bang isn't just about satisfying curiosity. It's about understanding the deepest nature of reality. Why does the universe exist? Why does it have the laws it does? Why is there something rather than nothing? These are questions that have puzzled humans for thousands of years. And thanks to Feynman and the physicists who followed in his footsteps, we're closer than ever to answering them. We may never know with absolute certainty what came before the Big Bang. The evidence may be forever hidden from us, washed away by the exponential expansion of inflation or lost in the quantum fuzziness of the early universe. But that doesn't mean we should stop asking, because in the pursuit of these questions, we discover profound truths about the universe and our place in it. Feynman once said, "Physics is like sex. Sure, it may give some practical results, but that's not why we do it. We do physics because we're curious, because we want to know, because there's something deeply satisfying about uncovering the secrets of nature. And the question of what came before the Big Bang is perhaps the ultimate expression of that curiosity." As we close, I want you to think about this. Every atom in your body was forged in the heart of a star. That star was born from gas clouds that formed in the early universe. Those gas clouds came from density fluctuations created during inflation. Those fluctuations were quantum events governed by the laws Feynman helped discover. You are literally made of quantum fluctuations from before the Big Bang. You are the universe made conscious, asking questions about its own origin. Feynman understood this connection. He saw that by studying the smallest scales of nature, the quantum realm, we could unlock the secrets of the largest scales, the cosmos itself. He showed us that the path to understanding what came before the Big Bang runs through the strange and wonderful world of quantum mechanics. The story of what came before the Big Bang is still being written. New discoveries are made every year. New telescopes peer deeper into space and further back in time. New theories are proposed and tested. The field is alive with excitement and possibility. And it all started with scientists like Feynman, who dared to ask the big questions and who had the courage to follow the answers wherever they led. So the next time you look up at the night sky, remember, you're not just looking at stars. You're looking back in time. The light from those stars left them years or centuries or millennia ago. And if you could look far enough, you'd see the cosmic microwave background,